Welcome back to your class. We are talking about conceptual model, and we identify the possibility to build a conceptual model taking into account the geological, hydrogeological, and of course hydrochemical data. And at the end you can arrive to a solid conceptual model which can be transposed in a model, in a mathematical model and numerical model, flow and transport model. In this case, also in our case, we realize a flow model, but taking into account the problem of the coastal area and of the marine intrusion, we mainly move to a density-dependent groundwater flow. It is very important if you are in a coastal area to take into account also the density-dependent groundwater flow. But it's not a loss of time. It's very important to have this density-dependent model because you can move to modeling the transport of the contaminant classes if you have a solid density-dependent groundwater flow system. The flow modeling we realize, of course, taking into account the characteristics of the aquifer, the hydraulic conductivity and the hydraulic gradient, the existence of the well, pumping well system, and of course of the vertical physical barrier, but the recharge of the aquifer, but at the same time also the losses from the main seawater canal. I mentioned you that there is some important losses in salt water from this canal used for industrial purposes. And of course there is we have to take into account also the marine intrusion. The flow model has been calibrated by the water table monitoring, and observed and calculated errors are very similar, so we can conclude that the model has a good calibration. The main error is about 0.4 meter, and correlation value is about 0.94, which is a very good value in terms of flow modeling. But what about the transport model, the density-dependent model? We realized the density-dependent model using the chlorides as a calibration target. The chlorides are very easy to identify and to analyze in groundwater, and of course they are very representative of the marine intrusion and the possible water losses from the sea canal. So we divide our density-dependent model in two steps. First steps which take into account the natural condition, so the pumping wells are not included, and the natural condition told us that the marine intrusion along the transit B and C are very small, so it's not an important process in the natural condition because of the high hydraulic gradient and the high flow coming from the groundwater into this system. But you can see that during the activity of the petrochemical plant before the realization of the pumping wells, of course there are the losses from the sea canal, and we simulate the losses from the sea canal you can see in the transit A. The second part of the density-dependent model include the pumping period. When the remediation activity started, the pump and treat system start to pump from more than 80 wells, and the results in terms of the diffusion and the concentration of the chloride into the system include, as you can see along transit C, the higher seawater intrusion due to the pumping activity and due to the existence of the physical barrier. But at the same time there are also the losses from the canal which affect a large part of the aquifer, starting from the shallow part, not from the deeper part, as you can imagine by the marine intrusion. And you can see the effect of these losses from the canal both along transit B and A. So we have part of the aquifer which are very interested by saline water, seawater, not coming from the sea but from the canal. The chloride non-reactive model has been implemented also in a transit mode, and to simulate what's happened in the our system after the pumping system start. So we can see in blue the classical fresh groundwater flow, and from green to red the higher concentration of chloride, which are which have three sources: the seawater, of course, the seawater canal losses, and another source is a natural old lagoon which has a high concentration in chloride, about to 15 gram per liters. We also realized this model to verify what's happened after the impermeabilization of the seawater canal. In 2010, this seawater has been interested by this intervention to reduce or cancel the losses from the canal. The situation simulated before the impermeabilization of the canal is that one. But if you look at the situation after 1 year after the impermeabilization, the model told us that there is a high reduction in the saltwater losses by the canals, and at the same time you can see here freshwater remaining area due mainly to the stagnation zone and the pumping wells. So we can see the losses from the canal we are reducing, the seawater intrusion in that area, of course, but also the effect of the physical barrier which isolate a down gradient area interested by a stagnation zone, and up gradient of this area we can see the effect of the pumping wells which inhibit the groundwater flow to the coastal area. So this situation seems to be very sensitive and very good, in very good relationship with the real situation we observe in the field. If you have a good calibrated transport model about chloride, you can use the same parameters for transport modeling to verify the distribution and simulate the distribution of your contaminants. In this case, we use the total petroleum hydrocarbon content, and starting from the chloride model, we realize a total petroleum hydrocarbon model. In this case, the sources are represented by the the persistence of the El Naples inside, over the water table into the site. And we also simulate the situation between 2010 and 2011. What's happened to the contaminant concentration? If you look at these slides, you can see the reduction of the contamination close to the area interested by the pumping wells. So the model told us that pump and treat system has a positive effect. As you can see, the red area here turns to yellow, which means that there are lower concentration. And you can see also along the depth that this situation is improving. Finally, after 1 year of simulation, we can affirm that our model indicated that plume is captured by the pumping system. But at the same time, an important action has been due to the marine intrusion, which is clearly affected by the chloride model, our coastal area and our pumping system. This reduced the efficiency of the pumping system because you are pumping not only the polluted groundwater but also some marine water coming from the intrusion. This model has to be calibrated before you can use for your remediation plan. And we calibrate the model about chlorides, and of course we also calibrate the model about the total petroleum hydrocarbons. How to calibrate? This is the slide that resumes the results of our calibration process, so I will describe you very carefully. On the left side you can see the results of the calibration about chloride transport model. On the right side you can see the results about our this model for total petroleum dissolved hydrocarbon. In the first graph we can see the good relationship between observed and calculated chloride concentration using the multi-level sampling system. If you look at the below graph, which take into account the relationship between observed and calculated chloride concentration based on the long screen piezometer integral depth sampling, so without using the multi-level sampling, we can see that there is no real positive correlation. So if you look at this graph, using only long screen piezometer to evaluate your chloride distribution without taking into account the stratification of this ion due to the marine intrusion, you can lead to wrong results, because it seems that your transport model is not a good model because there is no relationship between the data calculated and observed. But the problem is that the quality of the data you collected by integrated depth sampling, which has no good to evaluate the stratification of the ion or the contaminants in your system. If you look at the multi-level sampling in this graph, you can see that you can arrive to the conclusion that your transport model is a good model and you can use for your further purposes for remediation plan. The observed chloride concentration is very similar to the calculated one, so the transport model is a good model. What about the integrate and the results about the total petroleum dissolved hydrocarbons? It's the same. If you look at multi-level system, the model we realize, the transport model we realize has a good results. It's in good agreement between observed and calculated values. But if you look at the integrated depth sampling, the long screen piezometer sampling, the classical sampling, the model seems not to be so good. But I repeat, it's not a problem of the model. In this case, the problem is the quality of the data you use for calibrating your model. So the multi-level systems are very important and are necessary if you are looking for some stratified pollutants to build a solid transport model. To validate this model, you can also use an additional tool. You can evaluate not only the concentration of your contaminants and your chlorides into the aquifer by multi-level sampling, but you have also the pumping wells. If you look at the concentration of your contaminants in the water pumped by the wells, and you can refer to that in terms of mass recovery rate, taking into account the concentration at the discharge of the pumping wells. So if you look at the mass recovery rate, you have an additional tool for validating your model. We are not only taking into account the concentration in groundwater, but you have to also take into account the concentration, the mass recovery in your pumping wells. And also in this case, we observe that both for chloride concentration, as you can see in this graph, and of course also for total petroleum dissolved hydrocarbon, we have few information, lower level information, but we can state that this model, this transport model, can be not only calibrated but also validated in our system. So this model can be used for management plan and for remediation plan in the next future, and you can simulate in advance some scenario, future scenario, to verify what can happen of your site after improving your remediation activity with other techniques, for example. So it seems to me that we are close to arrive to a very detailed model and a transport model we can use by for further investigation and further remediation activity. But we have some additional tool that we can use also for independently validate our conceptual refining model, and we will see in a few minutes.